In our last class, we started this proof that if I have two convergent sequences, Sn and Tn, and I call their limits capital S and capital T, then if I add those two convergent sequences together, I get a third sequence, An, and this theorem establishes that that third sequence is also convergent, and it converges to the sum of S and T. So the limit of a sum is the sum of the limits, again, assuming that those two limits existed. In other words, assuming the original sequences were convergent. So the most important feature that I want us to focus on in this proof, I guess two things. The first is that the structure of the proof is exactly the same as the structure that we were using when we were proving the convergence for concrete sequences that had a formula that we could get our hands around, right? That's because in both of those proofs we're establishing the same definition, the definition of convergence. And so these same four pieces, for all epsilon greater than 0, there exists a capital N such that for all little n greater than or equal to that capital N, the absolute value of the sequence minus its limit is less than epsilon. Those four elements are exactly the same, and therefore the structure, the overall scaffold of this proof is exactly the same as it was before. The difference is where we get our capital N from. Here we are not going to get our capital N from doing algebra on a formula for a sequence because we don't have a formula for these sequences. They're abstract. This is going to apply to any sequences Sn and Tn. And so we have to get this capital N by appealing to the definitions of what we know about Sn and Tn, namely, we know that they're convergent. So we can apply the definition of convergence to those two sequences to produce our N somehow. So this is now our task, is to figure out how to bring this capital N into existence in a way that's a little bit different than what we did before. Let's go to the scratch paper. Because when we were proving convergence for concrete sequences in our previous topic, what we would often do was to start with the conclusion that we were looking for, which the conclusion for convergence is an inequality that looks something like this, right? That we want to try and conclude in our scratch paper. We would do some work on this to try and turn it into an inequality that gets n by itself, and then whatever quantity was over here, this became the inspiration for our capital N in the proof. Well, again, we're not going to get a formula. It's not going to be quite that simple as it used to be here. But I do want to start in the same place. I want to start by thinking about the inequality that we're trying to arrive at and try and do some work that can give us an inspiration for how to recover that inequality from what we're trying to do. For us, the inequality we're trying to arrive at is absolute value of An minus the quantity S plus T is less than epsilon. So let's use that as our starting point. So the role of Sn here is played by the sequence An. The role of the limit L is played by S plus T. And remember how our An sequence was defined in the first place. It's defined as the sum, the term-by-term sum, of the sequences Sn and Tn. So I'm just going to replace An with Sn plus Tn minus the quantity S plus T is less than epsilon. So all this is happening on a scratch piece of paper off to the side of our proof. Right? So we're not going to show these steps in exactly this order. So now is when we look at this absolute value and say this is really measuring a distance, right? Because every absolute value measures a distance. What distance is this absolute value measuring? Distance between what and what? When an absolute value measures a distance, it does so, let's say dxy, the distance between x and y. When an absolute value measures a distance, it does so as the absolute value of x minus y. So if we want to know what we're measuring the distance between, just cue in on the minus inside the absolute value. The distance between x and y is the absolute value of x minus y. So the absolute value of something minus something tells us the distance between those somethings. So what are we really measuring the distance of here?
Where the sequence starts and where it ends.
Yeah, so we're measuring the distance between the terms, the nth term of this sequence, if you like, where the sequence begins, right? Sn plus Tn, like, or whatever finite value of n that we choose, and the limit, the purported limit of the sequence S plus T. right? So that's what this absolute value quantity is measuring. It's measuring the distance between Sn plus Tn and S plus T. And the problem for us is that we don't know anything about that distance in this problem. But we do know something. What do we know the distance is between? Or maybe a better way to say it is, what do we know we can control the distance between in this proof? So the distance between Sn plus Tn, the nth term of our sequence, and S plus T, the purported limit, that's a distance that we don't know yet how to control. What distances do we know how to control?
Between Sn and S and Tn.
That's exactly right. We know how to control the distance between each of these individual sequences and its individual limit. We know we can control the distance between Sn and S. We know we can control the distance between Tn and T. We know we can do that because by definition, they're convergent sequences, and therefore, we can apply the definition of convergence by feeding any epsilon that we like into the convergence definition machine, and it will spit out for us a capital N, such that for all n greater than or equal to that capital N, the distance between Sn minus S is less than the epsilon that we fed the definition. Right? So we have control over this distance and over that distance. And the goal for us is to figure out how to rewrite this expression on the left-hand side here in a way that will convert it from a statement about the distance we don't know into a statement about the distances that we do know. And that actually is an algebra problem. How can I rewrite this absolute value so that instead of having Sn plus Tn minus S plus T in parentheses, we have some statement that tells me about the absolute value of Sn minus S, which we can control, and the absolute value of Tn minus T, which we also can control. What do you think? How should I work on this absolute value in order to discover out of it distances that we have control over? So the stroke of genius here is let's distribute that negative sign, that subtraction, across the parentheses on the S plus T. I'm going to take a moment and erase these less than epsilons for a moment, and just kind of start from the bottom here. This is equal to, if I distribute the minus, I'll get a minus S, and then I'll also get a minus T, right? And then, addition being commutative, as we know from studying the field axioms, we can just move the Sn and the S next to one another, and the Tn and the minus T next to one another. And it looks like we've made a lot of progress. Right? We're very close to having these two quantities that we want to control. But what's the missing step? What do I still need to do in order to get this to give me those two distances that I have control over? Right now, it still looks like one distance. What's my tool?
Absolute value of Sn minus S plus Tn, and then the absolute value of Tn minus T.
Right. We don't want this to be one big absolute value. We want it to be those two absolute values separately, Sn minus S, Tn minus T. And then what do I get in between here? Well, I probably want that plus to be in between here. But my question is then, what symbol do I put here? Is this quantity equal to this, or is it something else? What is it, in fact? Greater than or equal to? Less than or equal to? What theorem or fact are we using here? Name it. Claim it. Proclaim it. The triangle inequality. Right. The triangle inequality, which told us that for two real numbers, the absolute value of a plus b is less than or equal to the absolute value of a plus the absolute value of b. Triangle inequality. This is one of the reasons why we learn the triangle inequality is it is our tool for translating a distance that we don't know into terms of distances which we do know. Sometimes that required an add and subtract trick. In this case, it didn't. It just required us doing some algebraic simplification on the quantity that we were trying to control. So, triangle inequality, exactly. So, now we have rewritten the quantity which we don't have control over as being something which is less than or equal to the sum of two quantities which we do have control over. So let's look back at, if we invoke these definitions of convergence on Sn and Tn, whatever epsilon we feed these definitions, they're going to produce for us a capital N, which might be different, remember, between these two sequences. So we called them at the time N1 and N2. But for each of those capital N's, all of the little n's which are bigger will make the nth term of the sequence within epsilon of the limit of that sequence. So here's how I'm going to write that. Again, this is still on our scratch paper. This first distance, Sn minus S, will be less than epsilon. And the second one of these terms, the Tn minus T, will also be less than epsilon. So we'll be able to write less than epsilon plus epsilon. But my question is, when? When n is greater than or equal to what? So looking back at how we're invoking our definitions, when is the absolute value of Sn minus S less than epsilon? For all n greater than or equal to N1. That capital N which the definition applied to the S sequence gave us. So I'll put N1 right there. What about the Tn minus T? That we can say is less than epsilon, an absolute value, when n is greater than or equal to capital N2. So now this is the last thing that we need to figure out how to, well, a couple of last things that we need to figure out how to navigate. Is that in order to say that both the first distance is less than epsilon and the second distance is less than epsilon, I need both of these statements down here to be true. I need my little n from up here to not only be bigger than or equal to N1, but it also needs to be bigger than or equal to N2. And so here is where we ask the question, how do we choose a capital N, which we still haven't done for our proof, right? We still need to fill in this blank right here. How do we choose a capital N in a way that ensures that whenever little n is bigger than or equal to that capital N, we will be able to make both of these claims? So here's an illustration of two convergent sequences. Let's say that the green dots are my Sn sequence, and the purple dots are my Tn sequence, just for the sake of argument. The universe comes to us and it picks for us an epsilon. And we don't have any control over what that epsilon is. Maybe it's something really big, maybe it's something really small. But the epsilon that gets picked is going to be the epsilon that we ultimately have to use in both of our sequences. Right? So let's say epsilon is this 0.303 or something. Now one of these sequences, the ANs, kind of takes a while before it finally lands inside of that epsilon radius strip around the limit. The other sequence seems like it gets there really quickly and then remains. So, in other words, the role of our capital N1 in this example looks like it's being played by this number for the first sequence, that all the n's greater than or equal to N1 satisfy that that nth term of the sequence is within epsilon of its limit. Meanwhile, our N2, which is the n that's given to us by convergence of the other sequence, our N2 looks like it's considerably different. Right? For all n's greater than or equal to N2, that sequence gets within epsilon of its limit. Now, the question that we're up against is, what capital N should I pick that will make it so that both sequences are within epsilon of their limit past that point? How should that capital N relate to N1 and to N2? Or equivalently, where on this diagram do we find both of our sequences within epsilon of their limit? We find it after the largest of the n values. Right? If I'm before the smallest, then neither of my sequences is guaranteed to be within epsilon. If I'm in between the two of them, then one of my sequences has settled down to within epsilon of its limit, but the other one is still kind of dinking around. It's not there yet. And so it's not until after we pass the larger of the two capital N values that we know both of our sequences are going to be within epsilon of their limit. So how can I write that? This will actually look kind of like a formula. Capital N is just going to be the larger of my two n values. So I'll write it as the max of N1 and N2. Whichever of those two values is larger, that's the one that we're going to take. And we don't know whether n1 or n2 is going to be larger because we don't know anything about our two sequences, Sn and Tn. Right? And so we need a way of being agnostic, right? Not knowing which one of these two is larger, we still want to pick the one which is larger. So we say capital N is the max of n1 and n2. We can say in our proof that each of those is less than epsilon, not when n is individually greater than n1 and n2 respectively, but that both of these will be true when n is greater than or equal to, let's say, capital N, which is equal to the max of n1 and n2. Right? We need both of our sequences to have settled to within epsilon of their limit, and the way to do that is to force our little n to be bigger than the largest of n1 and n2. Then I add epsilon plus epsilon together. What do I get? 2 epsilon. All right. So there's actually one last thing that we want to do in order to make this proof look the way that we want it to. Ultimately, in our proof back here, we needed to end up not with 2 epsilon, but with a single epsilon over here in the corner. So we have to fix that somehow. All the algebra that we just did here didn't end up with an epsilon, it ended up with 2 epsilon. So how should we fix that? So I don't want to divide everything on the screen by 2. In particular, I don't want to divide this distance that the proof is asking for us to estimate by 2. But I definitely do want to divide this by 2. And that will require me then to also divide these by 2. But then once we cross this inequality symbol right here, maybe I don't want my division by 2 anymore. So, in other words, if I take out this 2 on the epsilon over here by dividing both of the epsilons before it by 2, epsilon over 2, then this inequality symbol, where did that inequality symbol come from? It came from the definition of convergence. Right? It came from right here and from right here. And the great news is the definition of convergence doesn't care what we feed into the top of that hopper. Right? Whatever we feed these definitions, it's going to provide us with an n1 and an n2 such that the distance between the sequence and its limit is within that number that we fed into the top of the definition. So if I want this number out here to come out epsilon over 2 instead of epsilon, all I have to do is feed the definition epsilon over 2 instead of epsilon. So that's how we fix that wrinkle. We feed epsilon over 2 into each of these definitions, and the definition dutifully provides for us an n1 and an n2 for which the absolute value of Sn minus S is less than epsilon over 2 and the absolute value of Tn minus T is less than epsilon over 2 respectively for little n greater than or equal to n1 and little n greater than or equal to n2. So the definition doesn't care what we're feeding into it. Epsilon was a placeholder. Right? Any number that we give this definition, it will give us a capital N such that our sequence is within that number distance of its limit once we pass that capital N. So that's how we make this all work. We're going to use these definitions applied not to epsilon, but to epsilon over 2. And then whatever n1 and n2 these definitions produce for us, we're going to take the larger of those two, and that's going to be our capital N. So let's finish writing all of this out. So what does this look like when it actually becomes a proof? So the first thing that we'll do is we'll appeal to these definitions. So by definition of convergence, there exists an n1 and an n2, both of them are natural numbers, that has the property that for all n greater than or equal to n1, the absolute value of Sn minus S is less than epsilon over 2. Right? So there's where we produce n1 as part of this proof. And then for all n greater than or equal to n2, absolute value of Tn minus T is less than epsilon over 2. Okay? So there's where we've plugged into these machines, plugged epsilon over 2 into these machines, and the machines have given us the n1 and the n2. And then comes the statement, the real triumph of this proof, let n equal the max of n1 and n2. So that's what ends up occupying that space in our proof. Then we say, let's let little n greater than or equal to capital N be arbitrarily chosen. Now all we have to do is prove this inequality, and that's where we go back to the algebra that we did on our scratch paper. And then this will finish the proof. Then the absolute value of Sn plus Tn minus the quantity S plus T is equal to, and here we're using the same algebra that we used on our scratch paper, Sn minus S plus Tn minus T. And then we apply the triangle inequality the way we did on our scratch paper, less than or equal to absolute value of Sn minus S plus Tn minus T. But because we know that little n is greater than or equal to capital N, which is the max of n1 and n2, that means that this clause is satisfied, n is greater than or equal to n1, and therefore Sn minus S is less than epsilon over 2. Less than epsilon over 2. But also, because n is greater than or equal to capital N, which is the max of n1 and n2, that implies little n is also greater than or equal to n2, and therefore this inequality is satisfied. And so Tn minus T absolute value is also less than epsilon over 2. And then when I add those two things together, I get epsilon, and that completes the proof.